All right, class. We left off last lecture talking about phase diagrams, and specifically we got to the point where we can actually construct fairly sophisticated phase diagrams for mixtures. Mixtures being solutions, solids, liquids, or vapors made out of multiple components. So specifically, we ended last lecture talking about liquid vapor coexistence in cases where I had some liquid, say down here, a vapor on top made out of some component A and B. So here's the liquid, here's the vapor, and in general, the composition of the vapor and the liquid need not be the same. And we worked out the thermodynamics, the rules by which we can determine the partitioning of those two components in those two phases. We can summarize our findings in a phase diagram, say in the temperature and mole fraction plane. That mole fraction goes from 0 to 1, and if we assume that B is more volatile, so B has a lower boiling point. So if I have pure B, its boiling point is down here. Pure A, its boiling point is up there. That a typical phase diagram for a miscible mixture of A and B, we might expect to look something like this, where we have a liquid at low temperature, a vapor at high temperature, and this region of coexistence, which tells us at a given temperature and mole fraction, say, of the liquid, what we should expect the corresponding mole fraction of the vapor to be. We even highlighted a specific example of water and ethanol, which its phase diagram looks slightly more complicated. In the temperature mole fraction plane, this is mole fraction of, say, ethanol, going from 0 to 1. Water, of course, has a boiling point of 100 degrees C. Ethanol, if you were to go look it up, has a boiling point of 78.5 degrees C. There's a liquid at low temperature, a vapor at high temperature, and in between, there are regions of coexistence. But what's kind of interesting, let's try that again, is that for the case of water and ethanol, there's a little more structure. There's a point here at 0.96 mole fraction of ethanol and about 72 degrees C temperature, known as a azeotrope. A point at which, at exactly this composition, both the liquid and its vapor have the same mole fraction, have the same amounts, relatively speaking, of ethanol and water. A consequence of this was, as we alluded to last time, the fact that you can't distill ethanol beyond that point. So that is to say that if we were to take a solution, initially dilute an ethanol, increase the temperature, we would generate a vapor enriched in ethanol. If we collected that vapor in some way through funneling it through some glassware, recondensing it, that would give a solution that we could then heat up again. It would then boil, producing a vapor enriched with a different composition, more enriched than its original liquid, which we could play again and again in this game until we get to this azeotropic point, by which we heat it up to cool it down. The vapor has the same composition. We can't collect that vapor and enrich and generate an enriched solution from it. So just to be clear, azeotropic means that the liquid and vapor have the same composition. Cool. Okay, so that's where we've been. The next question we want to think about through today's lecture is, how exactly does a system get from one phase to another? We've alluded to some artificial process by which we take a liquid, condense it, or take a vapor and condense it into a liquid, take a liquid, boil it into a vapor. I want today to think through more of the thermodynamics of that transition, and specifically infer some microscopic structures that must result as we transition between those two phases. And we'll think concretely about the case of a liquid vapor transition. So a way to remind ourselves of a liquid vapor transition would be to draw its phase diagram, temperature, and the order parameter for a liquid vapor transition is the density. I know that if I start at high temperature and low density, well, I'm likely to find a vapor there. At lower temperature, or certainly at higher density, I'll have a liquid. If I take that vapor and start cooling it down at constant pressure, I'll follow some isobar until I reach some point. Let's call that point the vapor density, that I will start growing in some amount of liquid until I reach some liquid density. And along that isobar, I'll then be able to further compress the liquid by cooling it down. There's a locus of these points forming the coexistence curve, where if I was to view the system, I would see it phase separated, big macroscopic domains of the liquid in contact with its vapor. Let's give this guy a little hand. Ooh, that's a terrible hand. Let's try that again. Now he'll wave to you all. Give him a high five. Okay, so what's important about this is that if I was to put myself somewhere in this region of coexistence, under this coexistence curve, what's kind of interesting is that in that region, it really highlights the fact that the system resists densities that are between those two endpoints. In other words, instead of continuously densifying the vapor to turn it into a liquid continuously, if I looked at the system under this coexistence curve, the system would actually rather form an interface between the vapor and its liquid and change the relative amounts by moving that interface, rather than have a state which microscopically had a density, a local density, which was intermediate to that liquid and vapor coexistence density. Now, that interface is going to come at a thermodynamic cost. So let's explore why that must be the case. So if I was going to imagine zooming into that region of coexistence where I have an interface, what color should our molecules be? Let's say that they're orange. So let's imagine up there are some sparse set of molecules in the vapor. Now, those molecules in the vapor, they're not interacting with any other molecules. The vapor is dilute. And so their free energy is largely just determined by the entropy that they have. And the entropy we know is just the number of states. And so those number of states reflect, in this case, just the number of different translational configurations that they can adopt. So we could say that they enjoy translational freedom. They're high entropy because they have many different unique microstates associated with many different locations in space that those molecules could be. Now, on the other hand, molecules in the liquid are much closer together. That's what we mean by a liquid. The density is higher. So those are our molecules in liquid. So they can't move around freely. They run into other molecules if they try to do that. So then why is the liquid stable? A liquid is stable because those molecules interact really strongly and attractively. So a molecule in this liquid, because it's surrounded by other molecules, enjoys favorable attractions. There's a lower energy associated with those molecules because of those attractions. So in some sense, in this sketch, coexistence is occurring because molecules can be happy either because they are enjoying favorable attractions or because they are enjoying high entropy, high translational degrees of freedom. Now that makes you worry a little bit about these molecules here at the interface. Those molecules can't translate freely. They still have enough other molecules around them such that their translations are hindered. And yet, at the interface, there are fewer molecules around them than there are in bulk. So they don't enjoy as favorable, attractive interactions. So it's not hard to imagine that those molecules are comparably kind of grumpy. They don't really like being there. From a entropic perspective, they have lower entropy because there are fewer translational states that they can adopt. From an energetic perspective, there are fewer other molecules around them, so they don't have as much favorable energy. So from both perspectives, the free energy associated with molecules at the surface should be positive. It should cost free energy to have created that surface. And indeed, that's true. Creating an interface costs free energy. There's a work required to create an interface, and let's call that work gamma little a, where that gamma is a parameter you have undoubtedly run into before. It's called the surface tension. This is what makes droplets out in the vapor spherical. You know, those droplets of aerosol, hopefully not coming out of all of your mouths, are, if you were to zoom in on them, roughly spherical because they're minimizing that interface, because there is a free energetic penalty to do that, and a droplet is the shape of minimum surface for a given volume. Okay. So there's a free energy penalty to create a surface. So then let's keep that in mind and then try to answer this question. What happens in time? What are the sequence of states as a system crosses a coexistence curve? So let's imagine now the pressure temperature plane. I have my vapor and my liquid. I'm going to start in the vapor and imagine transporting myself over to the liquid. I make an abrupt change in temperature such that I go from a region of stability, a region of parameter space where the vapor is stable, to a region parameter space where the liquid is stable. What happens? So if we're thinking about the states of the system over time, when I do that experiment, there's a couple different cases, a couple different scenarios you can imagine occurring. It could be one that, well, I start in the vapor, I know roughly what that's supposed to look like, and that the next state looks pretty similar, except for it's a slightly higher density. So if this was some rho 1, which is a uniform vapor, that what happens is that that density uniformly increases to some rho 2 greater than rho 1. The next step might be to slightly more increase that vapor to some rho 3 greater than rho 2. And then finally, to uniformly increase the density to some rho liquid, which is greater than rho 3. And let's say that rho 1 was the density of the vapor we started with. That's one way in which the system could transition from the vapor to the liquid, doing so uniformly throughout the system, gradually changes in its density to densities intermediate between the vapor density and the liquid density. Alternatively, it could be that I start in the vapor, and rather than increasing the density uniformly in space, what I do is, in the background of the vapor, I increase the density locally by a higher amount. So the row of the vapor, the density in the whole system increases in this next step, not uniformly, but because I have a microscopic droplet, that has a density equal to the liquid density. And if I add a droplet big enough, I will have increased the density by some amount, though it's not done uniformly in space. Then I can imagine increasing the density more, again, not by uniformly increasing the density, but by growing that droplet. So I still have the vapor being at its preferred density and a liquid growing in at its preferred density, and the total system density is increasing by increasing the ratio of the amount of liquid to the amount of vapor. Now, if I keep growing this, I can imagine forming, this is going to change of scale, an interface between a liquid and its vapor, which is now macroscopic. A macroscopic liquid domain spanning my whole, say, beaker, which then, if I wanted to go completely to the liquid, just grows that interface, brings it up to the top of the beaker, filling this with some rho liquid. So given our discussion of the phase diagram, the fact that when I put myself at densities intermediate to the liquid and vapor densities, the system really does resist having those densities, that it seems much more likely that the path the system takes as I do this quench, go from the vapor to the liquid, is through the process by which I increase the density not uniformly in space, but at the cost of forming an interface. So what can we say about this sharply? Okay, so let's do a calculation. Let's imagine we have a small droplet in the vapor at fixed temperature, pressure, and number of molecules. Let's draw a little sketch. So I have in a background of vapor a little droplet. Made out of some particles. Let's say that the size of that droplet has a radius of r, so its diameter is 2r. Let's say that at this instant in time, there are in vapor molecules. And in that droplet, there are in liquid molecules. Okay. So this droplet then is We've drawn it, at least it's spherical, and so we know what the surface area of that droplet is. Well, that surface area is equal to the area of a sphere. It's 4 pi. We gave a radius to our droplet as r, so 4 pi r squared. Now, the number of molecules in the droplet is something we can compute if we knew what the density of those particles were and their volume. And the volume of the sphere is just 4 pi over 3 r cubed. So note the surface area goes like r squared. The volume goes like r cubed. That implies that the surface area is something that scales like the number of particles in that droplet to the 2/3. Right. I could solve for r in this equation. R would be proportional to n to the 1/3. And if I plug in that over here, I'll find a scaling for the surface area that scales like n to the 2/3. If we want to say something microscopically, we are well equipped to do that. And the specific question we might ask is, what's the form of the probability to see this specific droplet, to see some specific number of particles in that droplet? And we are equipped to do that because we know that the probability of some group of microstates, of which n is a group, we could define a set of microstates in which all of which have n like molecules in some droplet configuration, and we know that that would be proportional to the partition function for that group, and the partition functions are proportional to e to the minus beta free energies. And if we work at constant temperature and pressure, the relevant free energy then is the Gibbs free energy. So the probability of seeing some number of particles in the droplet should be proportional to a Boltzmann factor of the Gibbs free energy of the number of particles, parameterized by the number of particles. So now let's work out an equation for this. So recall that we define the Gibbs free energy as E minus Ts from the extensivity of energy. We have that E is Ts, G is E minus Ts plus PV, of course. From the extensivity of energy, energy is equal to E, is equal to Ts minus PV plus, if I have multiple components, mu n. So this is just the energy. If I simplify that, the Ts's cancel, the PV's cancel. G is equal to a sum of the chemical potential of each component times the number of that component. And now we have to reflect on something. So this equivalency of the energy in its integrated form following from extensivity is true if we can neglect the fact that there's a change at the surface of some system whereby particles can interact differently. So in fact, extensivity was an approximation. It was an approximation that was a good approximation for macroscopic systems, but we're talking about microscopic droplets. So in general, there will be an additional term due to that surface. So this lets us write the Gibbs free energy. We have two components. We have a liquid particle, particles in the droplet. We have a vapor particle, and some number of them, of which, if n is being held fixed, n vapor must be n minus n liq. And those surface terms, well, we just worked out what the free energy to form surface was. It's some surface tension times some area. And if we wrote that area in terms of the number of particles in the droplet, that's that number to the 2/3, and there's some constant of proportionality. Okay, so let's rewrite this. So the Gibbs free energy therefore can be written as a constant from this constant n plus a difference in chemical potentials from minus mu vapor and plus mu liquid times the number of particles in the liquid plus this surface term. Where delta mu is equal to mu of the liquid minus mu of the vapor. So now let's think through that. If delta mu is positive, which phase is stable? So if delta mu is positive, that means mu liquid is larger than mu vapor. So which way will matter spontaneously flow? It will flow towards the vapor. That's a way of saying that the vapor is stable. If delta mu therefore is negative, that would mean the liquid is stable. That's the direction of spontaneous flow. And finally, if delta mu is equal to 0, well, that would be a statement of coexistence between the liquid and the vapor. Okay, so now we have a model for the Gibbs free energy as a function of the number of molecules in that growing droplet. So we're envisioning trying to say something about this droplet that's growing, has is accompanying its growth by aggregating some number of particles into it. From the relationship between the probability and the Gibbs free energy, we now can make statistical statements about the size and how that changes with the thermodynamic condition we're in, specifically the relative sizes of the chemical potentials of the liquid and the vapor. Okay, so let's think about a couple of different conditions. Let's start by asking, well, what size droplets am I likely to see under conditions where delta mu is positive? So let's try to draw out this free energy as a function of the number of particles in the droplet. So our equation up here, go ahead and highlight it. So the Gibbs free energy goes like that chemical potential difference times that number. So there's a linear piece in a linear dependence in the number of liquid particles. And then there's a piece that goes like into the 2/3 times some positive constant. Okay, so this is what a line would look like. That's the delta mu, which we've said is positive, times number of liquid particles. there's a piece that goes like into the 2/3. So if I sum those together, I'll get something that increases rapidly and then starts to increase linearly. Since the probability of seeing some number of liquid particles, some size of a droplet, is proportional to e to the minus beta, the Gibbs free energy, and the Gibbs free energy is positive and monotonically increasing, the most likely droplets are just over here. So we don't expect, under conditions where the vapor is stable, to see droplets that are sizable. The most typical size of a liquid droplet would be 0. That's where this is the smallest, where this Gibbs free energy is the smallest. In fact, fluctuations that grow droplets of larger sizes are really rare. They're rare by an amount that's e to the minus beta that free energy. Okay, well, that's in the case where the liquid is not stable. So indeed, if we tried to grow a macroscopic domain of liquid, it would take a large amount of work to do that. It would take a large free energy. It requires a large free energy to accomplish. What if we start to stabilize the liquid? So what if we consider a condition where delta mu is still positive, but close to coexistence, so close to 0? Or if we plot this, again, the free energy as a function of the number of liquid particles. So we still have a linear piece. Now it has a smaller slope. Let's even make that smaller. Make the slope pretty small. But we have a piece that scales like into the 2/3, still with that positive constant. So if I were to write this line in, it would still be monotonically increasing. Liquid droplets would still be very rare. And the reason for this is that the surface tension, this into the 2/3 piece, dictates that there's a large positive change in the free energy as I start to grow that droplet in. The fact that I have to pay to form a surface, to form an interface, which makes those molecules very grumpy. They don't have the low energy or the high entropy of any of the stable phases, means that even near coexistence, it's a really uphill battle to start growing a liquid droplet to grow a liquid droplet from these microscopic scales to something larger. So indeed, even at coexistence, if I look in the vapor around us, at equilibrium, I'm very unlikely to see any sign of the new phase. Okay, well, let's actually make the liquid stable. So let's consider a condition now where delta mu is less than 0, and draw the same plot. So again, the free energy as a function of the number of particles in the droplets. So now if delta mu is negative, there's a piece of the free energy that has a negative slope. That surface tension term still increases abruptly and is positive. So as I start to grow a droplet, it will still require free energies that are positive, but eventually into the 2/3 increases less quickly than linear in n. So this curve has to bend down and thus has a maximum at some value n star, and therefore has a barrier height we'll call delta G star. So even though the liquid is stable, it still has potentially a substantial barrier to transforming the vapor to the liquid, from growing a droplet of vapor particles, or of liquid particles in this vapor. And you all know that only fluctuations that are of the scale of kBt are fluctuations I'm likely to see. So if delta G is much, much larger than kBt, I might not actually see this transition happen. Even though the liquid is stable, thermodynamically, that's where it would like to be if given an infinite amount of time. If I start over here, I have to overcome a barrier to form that new state. Now we would call this droplet with n star size a so-called critical nucleus. At this point, if I started at that highest free energy state, I know that spontaneous fluctuations decrease the Gibbs free energy. So at that point, larger droplets will tend to grow and smaller droplets will tend to shrink. So in fact, if we were actually doing this process, trying to take a vapor to a liquid, what we would be waiting for, even in areas where the liquid is stable, is a rare fluctuation that takes the system all the way to the top of that barrier and then allows it to surpass this critical nucleus and then thus grow macroscopic in size. So this is a point that we will revisit later on in the semester when we actually start thinking about kinetics and how molecules actually move and what sets the time scales for those motions. But it's something I think you all have some intuition for from other classes. If you have to overcome energy barriers, the time scale for that sort of process depends on the size of that barrier. And so if that barrier is large, the time that I'll have to wait is large. Now, before we wrap up, let's reconsider this region exactly at coexistence. So let's plot this now, the free energy, as a function of number of liquid particles. So from up here, when the chemical potential is close to 0, the free energy to start growing that droplet is still positive. That's true even at exactly coexistence due to the surface tension. So exactly at 0, I should expect that Gibbs free energy to still increase. But eventually, that surface tension is going to stop mattering. I'm going to eventually grow a small droplet into a droplet large enough that I form a macroscopic domain. Now, at that domain, I could increase the number of liquid particles, not by changing the area, but just by moving the interface. So the free energy penalty to add some amount of liquid particles is 0 if I don't change the surface area associated with that that amount of liquid particles. Here, the surface area is the same, it's just given by this line, and the chemical potential to add more particles is 0. So in fact, the free energy to go from this state to this state is just a constant. Now, what happens if I go over on the other side? If I start from n particles in the liquid, so all the particles are in the liquid, well, I must have to do the same sort of thing. I start from a liquid, and I have to nucleate a little bubble, a little vapor, which will cost some free energy to form that interface, which will grow until it saturates at some largest value of the surface area. And so the free energy to transform macroscopically from the liquid to the vapor or vice versa is only determined by the surface tension. And when I grow macroscopically large, the surface tension does become a minimal or a decreasingly significant component to my free energy. And so that eventually flattens out. So we would say that this barrier at delta G is equal to 0, or at chemical potential is equal to 0, is exactly given by just that surface tension times the surface area of the entire droplet, of the entire system. Now, if this is a macroscopic beaker, that surface area for the entire system is enormous. So I'm talking about free energies that are macroscopic in size. If I put a macroscopic number up into the exponent of the Boltzmann factor, I'm going to get an incredibly small number. So let's actually work out what that would be for something like water in, say, a 1 milliliter cuvette. The surface tension for water turns out to be roughly 10 kBt per nanometer squared, which, if I have, which is the same thing as saying 10 to the 15th kBt per centimeter squared. So if I have a say, imagine now in one cuvette, I have a centimeter squared of area to form that interface over. Well, that would mean that I have 10 to the 15th kBt worth of energy that I have to overcome in order to, exactly at coexistence, go from the liquid to the vapor. That's an enormously large free energy and a very, very rare fluctuation. In fact, it's a fluctuation that would essentially never happen. What that leads us to then is exactly at coexistence, the initial phase, the phase you start with, essentially lasts forever. If I took a vapor and I put it exactly at coexistence, the size of fluctuations it would have to, the size of free energies it would have to spontaneously overcome in order to transition between that vapor and to the new liquid phase is enormous. It would take the age of the universe to see a fluctuation of that scale. Now, if I increase the chemical potential difference, making that liquid stable, I will drive down that barrier to the point in which you all actually see that. So in fact, if we go all the way back up to this first expression, or this first thought experiment, if we take this vapor, bring it exactly at coexistence, we'd wait forever. But the further we push it over into the region of stability of the liquid, the larger the chemical potential difference is that stabilizes that liquid, the smaller the barrier is, the more likely we are to see a fluctuation that could overcome that barrier. We will see shortly, the sooner that process will happen. Indeed, if this is now, this is pretty general. If we were to think about, say, ice nucleation, so taking liquid water and freezing it into ice, the same thing is true. If I park liquid water exactly at 0 degrees Celsius, it would take forever to see ice spontaneously form. But if I cool it cold enough, ice will form very quickly. And the reason why at coexistence we have to wait for such a long time is because we have to wait for a macroscopically large surface to be formed. So an interesting sort of thought experiment one could imagine is, what if we weren't trying to nucleate a liquid, or consequently a vapor, in a macroscopic cuvette? What if we tried to nucleate a liquid, say H2O, in a nanotube? So a nanotube, a very, very small test tube, very small beaker. You can imagine putting some water molecules in. Which has an area of a few nanometers squared. How long would I have to wait exactly at coexistence to see a spontaneous nucleation event, which takes the liquid from its vapor, or vice versa? That surface area is much smaller. That might be something one could actually observe. All right. Well, that's what I'll leave you for today. Have a nice spring break. I'll be posting a new problem set today, but we won't pick it up until at the end of the Friday after we come back. So whatever day that is. Okay, everyone stay safe and be well.